Hello there, and welcome back to the DAM. Today we will be modifying and overclocking this 386 to see how much performance we can squeeze out of it. And we will do so with the help of today's sponsor, PCBWay, but more on them later. This video is a continuation of my 386 series, and if you haven't already seen the first two videos, I will recommend that you do so before watching this one. Link is in the description below. Before we begin, let me first address some of the many comments that I have received on my previous video. Many have commented and said that these 386 upgrade CPUs that I use for this project are not real 386 CPUs and should be excluded from my testing. And to that I will say whether these CPUs should be classified as 386 or 486 is debatable. In my previous video I stated that the only true 386 in this video series is the AMD 386DX-40, and I still believe that to be true. But I guess by including these upgrade CPUs in a video about 386, I have indirectly classified them as 386 as well. Ultimately, I think it's up to each individual to decide whether to call a motherboard with a 132-pin PGA socket and one of these upgrade CPUs a 386 or a 486. For this video series, I will call it a 386.5 and include it in my testing. But since this topic is debatable, let's start off by doing an unboxing of one of these CPUs and see what the manufacturer has to say about it. And here we have the CPU that we are going to unbox and have a closer look at. It's the Cyrix CX486DRX2-50. A thing to note before we dive into this is that the manufacturer of these upgrade CPUs, and in this case it is Cyrix, would obviously have had their reasons to try and market and sell this as a 486 CPU. On the other hand, I'm sure that they would also have had some legal reasons to not call it a 486. During the unboxing of this CPU, feel free to pause the video at any moment if you have some text that you would like to read. I'm not gonna go over all text, but I will highlight what I find important. If we start by looking at the front of the box, we can see that they straight up call it a 386 to 486 clock doubled upgrade microprocessor. So the first line of text, they call it a 486. And down here we have 486 in a very big and visible font compared to the 386 in the background. So just looking at the front of the box, it's clear that they try and sell and market this as a 486. If we have a look at the back of the box, we have a lot of text. And as I said before, you can pause if you want to read it all. The text they have put in focus here is the text in purple. And it says that in just minutes, this Cyrix upgrade microprocessor takes your 386 computer to 486 class performance. So Here they call it 486 class performance, not a 486 CPU. So already here they try and get around the 486 claim, probably for legal reasons. And I have just been reading all the text, and nowhere on the back of the box they call it a 486 CPU. They keep using the term 486 performance. So they clearly know that for legal reasons they can't call it a 486, and they actually don't. Here they call it the 486 class performance, and over here they say that you can be up and running with 486 performance in no time at all. So 486 performance and not a 486 CPU. And that was all for the unboxing. Now we know a little bit more about this class of CPUs. So is this a 386 or a 486 CPU? I will let you be the judge down in the comments below. In the end, this video is not about classifying CPUs. It's about sharing my passion for old vintage computers. And I welcome you to call these CPUs whatever you find fitting. And with that out of the way, we can return to the topic of this video: modifying, overclocking, and testing these different CPUs in this 386 motherboard. And let's start with the modifying part. First thing I will do is wiring in this battery pack made up of 3 rechargeable batteries in Cyrix for a total of 3.6 volt nominal. It's not really a mod, just a convenient thing to have so that we don't lose all the BIOS settings when we are swapping CPUs. Next, I would like to be able to increase the voltage on the 5 volt rail, and for that I have made these two devices. I am not sure if I will need both of them, but now I have them. The first is one of these cheap ATX to AT adapters from AliExpress, where I have added some XT60 plugs. This is so that I can disconnect the 5 volt line from the power supply and feed in an adjusted voltage from my bench power supply instead. The other device for controlling the voltage is this little CPU adapter made up of 2 sockets. For the first socket, I have cut short all the 5 volt pins and soldered in an external 5 volt feed. I have also added this sense wire so I can monitor the voltage level directly on the CPU pins. For the second socket, I have just removed the 5 volt pins entirely. This will serve as a spacer between my modified socket and the motherboard, so that the external 5 volt don't feed into the motherboard's 5 volt. When we increase the voltage, we also increase the amount of generated heat. So I have this relatively heavy heatsink with a fan on top, and I can just place it onto the CPU like this. And with a bit of thermal paste and the weight of the heatsink, it should be enough to get a good thermal transfer. This heatsink can of course not go on top of the Blue Lightning 3 CPU. It already has a small heatsink glued to it. So for this CPU I will set up this violent fan to blow air onto the heatsink. And let me tell you, this CPU and heatsink gets insanely hot. So it really needs the high airflow this fan can provide. The final, and maybe also the most important modification we need, is a way to adjust the clock frequency for the CPU. In normal operation, this motherboard gets the CPU clock from a crystal oscillator like this one, and it provides a stable clock at a fixed frequency. And it is easy to swap the oscillator with another value to change the frequency. Unfortunately, these oscillators only come in a limited number of standard frequencies like 50, 60, 80 and 100 MHz. I would like to be able to adjust the frequency in much smaller steps, so for my project these crystals are not suitable. As a solution to this problem, I know that the YouTuber Athetas has created a programmable clock generator that is a direct drop-in replacement for a crystal oscillator, and it can even be configured down to steps of about 0.5 MHz. The catch with his anyclock, as he calls it, is that you need a good number of different reference crystals, and you also have to fiddle around with jumpers. But besides that, it looks like a good product, and I will encourage you to check it out. But for my setup, I would like something different. After searching the interwebs for some time, I found this small programmable clock generator on AliExpress, the SI5351. Apparently it is capable of generating frequencies up to 160 MHz in steps as low as 0.1 of a megahertz, and a suitable replacement for a crystal oscillator. It also features a rise time of only 1 nanosecond, plus it can be controlled by an Arduino. And for me, as a software developer, that sounds just perfect for my project. So I went ahead and ordered a couple of these oscillators and some Arduino Nanos. The only thing that is maybe not so great again is the output impedance of 85 ohms, but we will address that in a bit. And here it is, the SI5351 and an Arduino Nano to control it. I also ordered this tiny display that can also be used with the Arduino Nano to display the frequency. Now I just have to write some code and wire it up according to this very simple wiring diagram. And here we have the final result. I have put this Arduino on a prototype board, and as you can see, I have wired in this small display and our clock generator. I have also added this small control panel with 4 buttons where I can adjust the output frequency of the module in steps of 1 MHz or 0.1 MHz. And let's try and give it some power and see how it functions. If I can get this in the right orientation. I cannot. There we go. And I can see on the camera that the display is flickering, but in person it is not flickering. So just ignore that. And I can click the buttons, and here we can set the frequency. We can increase or decrease the frequency like this. And if I hold in the up button, this will go up to 160 MHz. Now the question, of course, is the output of this generator stable enough to drive a CPU? And to answer that, let's hook up the scope and see what the frequency looks like. Here you can see the output from the clock generator on the oscilloscope, and the signal itself looks to be stable at 80 MHz, but there is some kind of reflection going on, so I'm not sure about what that's about. But let's try and increase the frequency and see if the signal stays stable. And this is 110 MHz, and the signal is still stable. Let's go to 120, 130, and it still looks stable, but we still see that reflection down in the bottom, so I'm not sure about that. Let's increase the frequency a bit more. 140, and let's keep going, and at around 150 megahertz the signal breaks up. So I'm not sure about the 160 claim for this clock generator, but it seems to be reasonably stable at frequencies up to 150 or 149 megahertz. So it should be usable, but I'm not really liking the reflection that I see down in the bottom. So but when ordering these modules, I ordered from two different sellers, and I have a second one here. And although it looks to be the exact same generator, there is some subtle differences. The color of the PCB is not exactly the same, and the silk screen on the PCB is also not the same. So let's try and swap to this one and see if we get the same result. And I have now hooked up the other module from AliExpress from a different seller than the first one. And as you can see on the oscilloscope, for this clock generator, we don't have that reflection going on. So there is some differences between these modules. But let's try and increase the frequency for this module and see if it will do 160 megahertz. And so far it's looking more sharp and more stable than the other module, so that's a good thing. 135, and as you can see, around 136, 137 megahertz, this module starts to break down, where the other could do up to 150 megahertz. But I like this module more than the other because it doesn't have that reflection going on, and overall it seems to be more stable. And 150 megahertz, no, I mean 135 megahertz should be more than enough for our overclocking project. So I think I'll go with this module. And now you know that if you are ordering these clock generator modules on AliExpress, there are some differences between them, although they look to be the same. I will link in the seller I bought this second module from, and also the one I bought this first module from, and you can decide which one you would like to order if you need one. Now that we have an adjustable clock source, you might think that we are ready to plug it into our motherboard. I mean, after all, the listing on AliExpress calls it a crystal oscillator drop-in replacement. And I have of course tested that, and I can tell you that this module does not have the signal strength to drive a motherboard like this. So to use this clock generator, we first need to amplify the signal, and for that I have put together a small amplifier in KiCad. So now I just need someone to manufacture my prototype, and that is of course where today's sponsor comes in. PCBWay is your all-in-one manufacturer for PCB prototyping, CNC machining, 3D printing and much more. With their PCB prototyping service, they offer rapid turnaround and prices for 2-layer PCBs starting from only $5. And you don't have to be an expert in PCB design to order from PCBWay. With their shared projects, you are only one click away from ordering your next PCB. Here you will of course also find my shared projects, where you can order the PCBs that I have created here on my electric dam. I use their PCB prototyping service all the time. It's both fast, convenient and cheap. And I have of course also used it for today's project, so let's have a look at what we got. I have just received my order from PCBWay, so let's go ahead and open up this box and see what we got. Very exciting. And we have some foam packing. And here we have our PCBs. And what is this? Okay, it's some very big stickers, but very nice. I think it's a sticker. Yes, it is 2 big stickers. So I have to find some place on my wall to put them on. And we have a receipt. Let's put that away. And 2 more stickers. Very nice. Thank you, PCBWay. Let's get the box out of the way, and why not put the sticker right there. And here we have my amplifier prototype. Let's open it up. And get it out of the bubble wrap. And let me just set up the camera so you can have a closer look at it. And here we have my little PCB prototype. As you can see, I have ordered it in yellow and with black solder mask. And on the back here you can see that I call it the clock stick, and it only uses through-hole components. On the other side we have the beaver in black, and I will say that this beaver in black looks pretty creepy. I would normally go for white, but I thought yellow and black sounded like a good color combination. But I should have done this silk screen in white. That beaver is just a bit too creepy, but whatever. This is just a prototype, so I can change the solder mask to white if I end up making this a product and not just a prototype. But let me assemble one of these sticks, and I will tell you more about the idea behind it. Here we have the assembled prototype, and it's basically just a carrier board with a single transistor amplifier. The transistor I have used is the 2N3904, and according to the datasheet, it should be able to handle frequencies of up to 200 MHz. So it should be suitable for this application, but I am not sure it will work, but we will give it a try. Here we have the full setup with the clock generator connected to our control panel, and the idea is that the 2 output pins will connect into the socket where the crystal oscillator was installed, and it will sit in the board like that, and you can adjust the frequency with the controller. But I have tested this board with my oscilloscope, and this single transistor amplifier, it can't handle the high frequency, and I was a bit afraid of that. So designing logic with discrete components like this is definitely not my strong side. I really don't know what I'm doing here. I'm just it's just trial and error. So this board clearly needs some more refinement to work. Maybe an integrated amplifier would be a better idea for this board instead of the single transistor. But looking at the datasheet, I just thought that okay, this is rated for I believe 300 megahertz, so up to 160 should be no problem, but there is clearly more to it than this. So but if you have any idea to how to improve this board without putting an integrated amplifier onto it, I would love to know about it, so let me know in the comments if you have any suggestions. Maybe another model of transistor could make this work, but for now I think we have to go to plan B. And this is my plan B. I will cut open this crystal oscillator with my Dremel, and I will remove the quartz resonator inside the enclosure, and instead I will feed it the signal from the clock generator I got on AliExpress. And let's see if this can work. And here we have the final setup. I have hooked up our modified oscillator to the clock generator with an coaxial cable, and I have also hooked up 5 volts from my bench power supply. In normal operation, the oscillator will get the 5 volt from the VCC pin on the motherboard, but for testing on the bench I hook up an external 5 volt. And I have also hooked up the scope so we can see what the output of the oscillator is when we power it on. And let's just do that now. And here you can see that we have a very clean and very stable 80 megahertz. So far it's looking very good. But let's see what happens when we crank up the frequency on our control module. And let's crank it up to 100 megahertz. And as you can see, we have still a very clean and stable clock signal. Let's try and go up to 120. And still, it's very clean and very stable. So I think there is a chance that this actually might work on our motherboard. And 130 megahertz is also it's still very stable and clean. Now we go to 135 megahertz and it is still doing it. But as we know, this oscillator cannot deliver a clean output signal above 135 megahertz. So of course it starts to impact the final output from the oscillator when we go above 130 megahertz. But we don't need to go that high anyway for our overclocking. So now let's try and plug this modified oscillator into the motherboard and see if it can run the 386 CPU. A final thing I would like to say before moving on to the testing is in relation to this adapter that I showed you earlier in the video. After testing it and also reading up on how an ATX power supply works, I have come to realize that this adapter is no good. This is not going to work as I thought it would. And there is of course a good explanation for that, but it's a whole nother can of worms that I am not going to open in this video. So the overclocking we will do in just a second will be at 5 volts only. The overvoltage part will have to wait for the next video in this series. There is also the memory part of this project. The RAM sticks I have here is rated for 70 nanoseconds, and I think we need something faster, but that will also have to wait for the next video. And with that said, let's move on to testing. And here we have our final test setup. I have plugged in our modified oscillator, and it is now controlled by our control module. And you can follow along on my second camera here, so you can see what frequency we are running at. Remember that the CPU is running at half the external clock frequency, so 80 megahertz on the display here will mean 40 megahertz on the CPU. And the CPU I have plugged in is the AMD 386DX-40. So let's see how much performance we can get out of this setup without increasing the voltage. And first let me just check what we have for wait states, and we have 0 wait states. So that's probably what we want to have. So let's just boot it. Let's start at 3D bench for fast PCs and see what we get on our base clock of 40 MHz. And for our base clock of 40 MHz, we got 15.6 frames in 3D bench at for fast PCs. And let's run the Doom demo and see what we get there. And this is the max detail. No need to run it in low detail, because who wants to play Doom at low details in a postage stamp sized screen? And this will take some time. And for the Doom at high detail, we got 6.75 frames. So quite a bit of a slideshow, but that was to be expected. Let's increase the frequency, and I think let's start by going to 88 MHz. That would be a overclock of 10%. And let's see what that does for us. And for a 10% overclock, we got a few parts more frames in 3D bench. Let's do the Doom also. And in Doom, we also got a small increase in FPS from our 10% overclock. Before we increase the frequency more in 3D bench and Doom, let's go to landmark system speed and see how much we can increase the frequency without needing a reboot. So let's just go to 89 and 90 MHz, and it is still running. 91, 92, 93. Okay, at 93 MHz the computer froze, so we will need a reboot before we can run it at this frequency. Let's see if it will boot with 93 MHz on the clock generator. And it does. So I think we can go a bit higher. Let's go to 96 MHz and run our benchmarks. If the computer boots, of course. And again, we got a improvement. Before we do the Doom benchmark, let's just find out how much we can increase the frequency before this motherboard will no longer boot. Let's try 100 MHz. That would bring the CPU frequency up to 50, and that is not booting. So let's bring it down a bit to 98 maybe. Let's see if we can run the DOS bench, the 3D bench at 98, and no, the computer froze. So let's try the 0.1 MHz adjustment. Let's go down to 97.5. And at 97.5 MHz on the clock generator, we got 18.5 FPS in 3D bench for fast PCs. Let's try and set it at 98 and see if we can boot. And at 98 MHz the computer froze. So let's go down to 97.8. I think we are right on the limit of what this motherboard can run without any increase of voltage. And it froze again. So let's go down to 97.5 and see if it will boot with that. .5 frames at 97.5 MHz on the clock generator. Let's try the one for slow PCs. And we get 18.8 frames. Let's try Doom at the high detail. And it immediately froze. So let's try and add a wait state and see if that will make it run Doom. And it gives us the same result. So let's try and go to 98.5 with one wait state. And let's see if we can run the... No, it froze. So I don't think we can push this motherboard with the 386 DX40 any further than this. Let's do one final thing, and let's go back to the stock 80 MHz clock. And I'm curious how much I can increase the frequency while the system is running. And let's do the landmark. And let's just increase the frequency. 90 MHz, 92, 93, 94. Let's try and exit and run DOS bench. Oh no, 3D bench. Jesus, I might have mixed up some names in this test, but just ignore that. I called DOS bench for 3D bench and 3D bench for DOS bench and so on. So yeah, just ignore it. And one wait state. Let's try and increase it a bit more. And let's try and run it again without reboot. 18.8. Let's try and increase it with maybe 0.5 MHz. Okay, we got 0.1 of a frame more. Let's go to 97. And it seems like changing the frequency while the system is running is is working reasonably well. It seems like if you change the frequency more than around 8 MHz while it's running, it will crash. But so far it's doing it. And for the final run for Doom on the 386, we got 8.19 frames, and I think this is the best I can do right now without increasing the voltage. So this is the final result, at least for now, for the quote-unquote real 386. So let's move on to some of these contested upgrade CPUs. And now I think it's time for a quick summary and a conclusion to end this video. As you saw, we managed 34.6 frames in 3D Bench with the Blue Lightning 3 running at 117 MHz, and that is a decent result, I would say. For the Doom benchmark, we didn't get good results, but for the playtest, we did better. Although I had to lower the frequency a bit to make the Sound Blaster run stable. I am not sure why the Doom benchmark was running so slow compared to the playtest, but let me know in the comments below if you know why that is. What I didn't manage was getting the 486 SXL to run with level 1 cache. I have tried different settings for the Casio tool, but it did not change anything. So that is definitely something I will have to investigate in the next video, and it will probably include some BIOS modifications. Another thing we didn't manage was increasing the voltage, so in the next video I will modify an ATX power supply so we can adjust the 5V rail. In the next video we will also take a look at some faster RAM and other miscellaneous optimizations. In any case, that is all I have for you today. I hope you liked this video, and if you did, don't forget to hit the like button. Also remember to subscribe to my channel if you haven't already, so you don't miss the next installment in this series. And I will see you in the next video.